Okay, here in this video I'm going to show you solutions to several of the problems from homework 3. And the first one is number 1, and it shows this FSK signal encoding some bits, and it's a BFSK modulation, so we have a digital signal which takes on values 0 and 1. Okay. And there are two different frequencies. So we have a lower frequency when we have a 1, and we have a higher frequency when we have a 0. And it asks to calculate the bit rate, find the center frequency, and find the difference frequency. Okay. The difference frequency, according to the definitions in the text, is actually half of the difference between the two frequencies. And it's this FD value that's used in coming up with the equation for the channel plan. In any case, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 bits in 14 milliseconds, meaning we're sending 1,000 bits per second, or 1 kilobit per second is the bit rate. The center frequency, we look at 1 millisecond and we see 2 complete periods. And so we have half a millisecond is the period, or 500 hertz for frequency number 1, or maybe that's number 2, the higher frequency 1, that's the lower frequency. And frequency number 2, if we look here, we have 1, 2, 3, 4 complete cycles in 1 millisecond, so that's 250 hertz. And starting with those calculations, okay, so we have the 1 kilobit per second for part A. We have the 2 kilohertz and 4 kilohertz frequencies. And now we find the center frequency, which is the average 3 kilohertz. And now FD is actually half the difference, and it's 1 kilohertz. Okay? So that's problem 1. Problem 2 is very similar, except we have slightly different thing going on here. In fact, we've sent 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bits in 20 milliseconds. And so we're sending 1 bit every 2 milliseconds, so that's 500 bits per second. And if you look at the frequencies here, you'll see that we have 2 periods per bit for the lower frequency. For the higher frequency, we have 1, 2, 3 periods per bit, looking at this little section here. And so that gives us this following calculation. A bit rate of 500 bits per second. We had 2 cycles in 2 milliseconds for the low frequency and 3 cycles in 2 milliseconds for the higher frequency, giving us 1 kilohertz and 1.5 kilohertz. The average of those is the center frequency, 1.25 kilohertz. And FD is half their difference, or 250 hertz. Okay, so that's problems 1 and 2. Let's see if I can get you through problem 3 in this same video. Here it is. We're given a bit rate of 1 megabit per second. And we're told that we have 32 symbols in our alphabet, and asking what the baud rate is. And basically you have to calculate, we use the symbol M for the number of symbols in the alphabet, and then L, the bits per symbol, is log 2 of M, and that's 5 bits per symbol. And the baud rate is lower than the bit rate by a factor of L. One has units of symbols per second on the left here. The bit rate is bits per second, and the denominator is bits per symbol. And so that gives us 200 kilosymbols per second, or 200 kilobaud. Let's keep moving right along and do problem 4 here. And in problem 4, they give us an MFSK system with M equals 8 and a bit rate of 1 megabit per second. First thing asked for is the baud rate. And I'm going to take the log base 2 of M and get 3 bits per symbol. And then the baud rate, again, is lower than the bit rate by a factor of L, which is the number of bits per symbol. And so I get 333 kilobaud for the baud rate. Now it asks for the minimum separation between FSK channels. Stallings has an equation given on page 133 that says that the minimum spacing is 1 over the symbol period, and that's on page 133. And so the minimum frequency required is 1 over TS, yeah. And that means that the baud rate itself is the minimum frequency spacing. So instead of writing 333 kilobaud, I'm going to write now 333 kilohertz. Okay, and this minimum spacing happens to be twice the FD value. Remember, FD is half the channel spacing. And then it says, okay, let the center channel be at 12.5 megahertz. Calculate those 8 frequencies. Well, we're going to go ahead and use this equation for the frequency number I. Is the center frequency plus a constant times the frequency difference. And you can see that this factor of 2 here means that as I increments by 1, f of I increments by twice FD. And we can plug in and get 11.333 megahertz, 11.666 megahertz, 12 megahertz, 12 and a third megahertz, 12 and 2/3 megahertz, 13, 13 and a third, and 13 and 2/3 megahertz. Okay, so those are the values I have for problems 1 through 4. And I'll stop this video here. Hope that helps.